Next, with a small change, I can convert this procedure for in-order traversal. So let us look at in-order traversal. Let us see in-order traversal. In-order traversal says first go to the left child, then print, then go to right child. So left, root, right, that's how we read it. Let me quickly trace this and show you. We need a stack and we start from root, then. So initially that T is not null and the stack is empty. Now let us look at this pre-order. See, pre-order, first if T is not null, yes, first step is printing. But in order, first we go to left child. Then we should not print. Okay, let us move to left child. But as per pre-order, first push the address and go to left child. Okay, push the address of that 8 and go to left child. Okay, we will go do this. Then again T is not null, print. We will not print. This step will not perform. Push and go to left child. Push the address of 3 and move to left child. Okay, move to left child. Then this is not null again. So push the address of this 4 into the stack and go to left child. Now this is null. If it is not null, these steps we are performing, we were not performing this printf. We were performing 2 steps. Now it is null, else part. So in this pre-order, what we are doing? Pop out, go to right child. Watch here. Pop out, we'll get the address of 4. Now before going to right child, we should print. Before going to right child, we should print in order. So printing should be done now. We are about to go on right child. See this, about to go on right child. So before that, first you print. So it means I should print here first. So print this first, then move T to R child. So printf is removed from here. That's all. So with a little bit of observation, I can say that in pre-order, before going on left child, we were printing. But in order, before going on right child, printed. So this function becomes in order. So a minor change has made it in order. That's all about in order. One thing I want to show you, what is the time complexity of this function? In pre-order also we saw, and in order also, same function, just a change of position of printf function. Just a minor change is there. So what is the time complexity? Loop is there. Loop. How long? As many nodes are there, that many times it will repeat. So what is the time complexity? Order of n. Order of n. And what was the size of the stack? Depends on the height of a tree. Yes, stack depends on the height of a tree. Now post order. Post order is little complex. So I'll keep the same code. Let us see what about post order. Let us see post order. Post order says that first go on left child, then right child, then print data. Go to left also, right also, means you should not print here. So after finishing both left and right, we should print. So let us take a stack and trace this one. So I'll take a stack, start from here. See, the procedure will be similar to this one only with some changes. So what changes required there? To study that, we will trace it with the help of that function only. Actually, the function is for in order. But where we require changes, we will make the changes there. So I will follow that procedure only and trace it. So let us start. T is on this one. So T is not null. What is the first step? Push the address of that node into the stack. 8. Then move to left child. Okay, move to left child. So T is not null. So if it is not null, push and move left. So push the address of 3 and move left. Push the address of 4 and move left. No, it is null. So null means what we should do else? Pop out, print and go to right child. So let us do it. Pop out. So this is deleted. T is here. Print and go to right child. No, don't print. Post order means first go to right child. Afterwards print. Left child over right. Go to right child, then print. So we should not print this one. We should not print. It should not be printed. Pop out and go to right child. Okay, I will go to right child. I'll go to right child. So right child is what? Null. If it is null, pop out and go to right child. So which one I get? Address of 3. Oh, 4 I did not print. I should print that 4 also. That's it. So the difference is I should push that address of 4 once again. First time it was pushed so that we can go on right side. Second time we need so that we can print it. So before going to right child, push the address of that 4 once again into the stack. Once again push it. Then go to right child. So I will write down the code afterwards. So push it again and then go to right child. Now T is null once again. Pop out. Whose address we get? 4's address. Now see the second problem. Second problem. First time we pop out, that was for right side. This time we are popping out, this is for printing. We are back on 4. Now we should print. Now how to know that that address was for right side and this address is for printing? There should be some difference. Yes, this is the problem. So what we should do, when we are pushing it second time, we should push negative address. Addresses cannot be negative. No, you convert that address into an integer and store negative integer. When you are using, convert into an address, positive address. Okay, we can do that. So push the address once again. So both the time, first time when you are pushing, push positive. Second time when you are pushing, it is negative. So positive address means go to right child. Negative address means print the data. So I will directly modify that one and you have to trace the complete working on this example tree. Okay, this is sufficient. If I explain, it will be confusing, right? So you take pen and paper and trace this function. So I will directly write on the function. So I have explained you important points in this one, that we have to push the addresses 2 times. So I will write on the code, right? That's all. With that, I will finish. Tracing you do. You take an example tree and you trace everything and generate the complete output by yourself. So that is a student exercise. I am writing the code. Pop out an address from the stack. As I said, the stack will be of integer type. So I will take one long integer, a temporary value, temp. Okay. So I will pop out a value from the stack, pop st. So I will get an integer value in a temporary variable. Now check whether it is positive or negative. If it is positive means we have to push again and go to right child. If it is negative means we should print. So first check if it is positive. If temp is greater than 0 means positive. If it is positive, then do what? Push the negative value of temp into the stack. Push the negative value into the stack. Then move to right side. Temp is having an address, but actually it is integer value. I typecasted it into an address. Then caps r child, that t is moving on to its right child. Okay, this syntax I have written. Let us see how it works. Okay, while writing the program. Once again, if the address is positive, push the negative address once again and move t to right child. If it is not greater than 0, means else means it is less than or equal to 0. Anyway, it will not be 0 here. So it is less, negative. If it is negative, then what we should do? Print the data and again make t as null. So print data. So print data by typecasting that numeric value into address. So print the data and make t as null. So this is the extra work required for post order. We have to push the addresses 2 times, one for going on right side, one for printing. So positive and negative addresses we are pushing. This is the extra work that we require in post order traversal. So that's all with the iterative version of tree traversals.